All right, Eric, you sent me an interesting problem. I'm going to do my best to solve this for you. I've worked on this problem a little bit yesterday, and I was unable to solve this problem without making certain assumptions. And the interesting thing is based on the assumptions I made, there was two different ways to solve this, based on two different assumptions to get two different answers. So I'm going to show you the way that I think they want you to solve it. I'm also going to show you the other way, and we're probably going to have a little bit of a conversation about this piece. You might want to talk to your professor as well. I had to look up this notation. This notation is not a standard math notation. This is more, I guess, ironworker industry notation. And what I found is that little circle with a line through it means diameter. So here we have a diameter of 1 meter. And it's pointing to the larger circle, so we're talking about the larger circle here. And for this one, we have a diameter of 15 millimeters. For that smaller circle. Okay, and let's talk about an assumption that I had to make here. Okay, we're asked to find the distance of this line between the center of this circle and the center of this circle. One assumption I had to make, if I were to take a line and I were to draw a line tangent to the edge of this circle, right? So it's touching just touching the edge of that circle at that point, right where the diameter goes through, and I were to extend that it would also be tangent to the larger circle. And then if I were to go ahead and do the same thing on the other side, I would have the same thing. Okay. And why would I want to do that? Well, if you look at this right here across the middle, this is the diameter of the circle, and you can see these two lines here are two vertical parallel lines. So this distance right here is the same distance, for example, as this distance all the way through right here. Well, that happens to be the distance of the line that we're looking for plus the radius of this circle plus the radius of this circle. Okay, which means that my diameter of my larger circle, which is 1 meter, if I were to subtract off this distance here, which is one radii, okay? So the radius here, so if the diameter is 15 millimeters, then the radius is half of that. The radius is going to be 7.5 millimeters. So I would subtract off 7.5 millimeters and another 7.5 millimeters. So essentially, I'm subtracting off a diameter. I'm subtracting off 15 millimeters. Now, I can't just do that without doing some unit conversion. Okay, so let's convert both of these to centimeters. 1 meter is equal to 100 centimeters. Okay, I'm going to take that 100 centimeters and I am going to subtract off my 1.5 centimeters, because that's the equivalent of 15 millimeters here, to get a total of 98.5 centimeters. Okay, and that would give us an answer for part 1. Now, I'm not going to show you the other method other assumption that I made until after I've completely solved this problem using the first assumption. Because if that assumption is correct, and in fact I can do this and that these are tangent, then okay, that would follow. That would be fine, and we would have that line segment there, that chord is 98.5 centimeters. So we didn't really use any trig or anything, but we used the fact, we used both of these numbers, both of these pieces of information that we're given. Now, if we move on to the second part of the question, that's not the second part of the question. See, there's that symbol I was telling you about there, right there. So I had to look that up. So let's see here. Well, you know what? We'll use the same picture here. Okay. So I'm going to go ahead and I'm going to label this to be 98.5 centimeters. Okay. The second question we were looking for was what is the arc length? Actually, that's what I have written right here, don't I? Yes, this was the second question. Okay, well, we want to know what the arc length was. So regardless, okay, we want to know what this length is here. Okay, and in order to know what that length is there, we need to know the following. I need to know if I were to take a line from the center of this circle and put it out to that end point of the chord, line from the center of the circle, put it out to that end point of the chord, what is this angle going to be? Because if I know what this angle is, I will know what percentage of the circumference of the circle this is. Okay. Well, what do I know? I know that this is 98.5 centimeters. I happen to know that if the diameter here is 1 meter, that the radius is going to be half of that, 0.5 meters. Okay. So we're talking about 0.5 meters. 0.5 meters is the same thing as 50 centimeters. So I'm going to do all this in centimeters. So I have 50 centimeters here. I have 50 centimeters here. What do I have? I have a triangle where I know all three sides, and I'm looking for this angle right here. Okay, if you ever have a triangle like this and you have all three sides and you're looking for an angle, you can use something called the cosine law. Okay, and the cosine law tells us that a squared is equal to b squared plus c squared minus 2bc cos of a. All right, well, what does all that mean? Well, this would be my angle A. Okay, and the other A's, the lowercase a, lowercase b, lowercase c, are referring to sides of the triangle, and this is the small a is always going to be opposite of the angle A, and b and c, it doesn't really matter which one's which in this case because we can just arbitrarily choose those. So let's just say here that this is going to be b and this is going to be c, and we're going to have to plug in those numbers to the formula and solve for the angle A to get that angle. So here comes our trig. Well, I'm actually going to just solve for cos A with this formula first, and then I'm going to plug in the numbers. So let's have a look. I'm going to bring the b squared and c squared over to this side. I'm going to get a squared minus b squared minus c squared. Okay, I have to subtract b squared and c squared from both sides. That's going to be equal to negative 2bc cos of a. Okay, and then I'm going to divide both sides by negative 2bc. And that will get rid of this BC here. And so I'm left with the cosine of A is equal to A squared minus B squared minus C squared all over negative 2BC. And how do I find A then? Well, that just means that A is equal to the inverse cosine of A squared minus B squared minus C squared all over negative 2BC. Okay, so you could even write that down, as a formula, right? If you wanted to, if you're looking for an angle. Oops, I drew a line there. I forgot that. It's touch sensitive as well. So what are my numbers? Well, I said here that I have 50 centimeters and 50 centimeters are BC and 98.5 is A. Okay. So I have A is equal to the cos inverse of, let's see, what was A again? 98.5, right? So 98.5 centimeters squared minus 50 centimeters squared minus 50 centimeters squared all over negative 2 times 50 centimeters times 50 centimeters. All right, and I plug all that into my calculator for the to find my angle here. Okay, so let's see if Windows has a powerful enough scientific calculator here so that we can do this. Let's see, there's my scientific calculator here. Looks like I at least have a squared button. So we got 98.5 squared minus 50 squared minus 50 squared. Okay, so what is that going to give us on top here? We're going to get 4,702.25. Okay, and on the bottom, I have negative 2. So we got 2 times 50 times 50. Okay, and negative 5,000. Okay, so I'm looking, so A here is equal to the cos-inverse of this whole ugly thing here. Okay, well, what is that ugly thing? Well, I have 4,702.25 divided by negative 5,000. So that's negative 0.94045. So we're looking at the cos-inverse of negative 94045. Right? Okay. And let's see, inverse. Okay. So I believe yes. Okay, so there's the inverse button there. And for you, if you have a graphing calculator or something, it's going to be completely different, right? You're probably going to punch in that number first. So here we got cos-inverse. Okay, and that gives me 160.127 degrees. Okay, so A is equal to 160.127 degrees. Okay, so then I come back up here, and I'll be real honest with you, this does not look like a 160-degree angle. Okay, so 160.127 degrees. Okay, 180 would be fully flat. I'm going to show you the other method here because the other method actually looks more accurate with respect to the image, but it doesn't use this other piece of information here. So I'm not sure there's assumptions that need to be made here. Okay, so so I have the angle. Well, I also have the diameter being 1 meter. Okay, which means I can find the circumference of that larger circle. So the circumference of a circle is pi d, or in this case, pi times 1 meter. Okay, so it winds up actually being pi meters. Now, I believe that in the Ironworkers manual I was looking at, they like you to use 3.14. So what we can say is this is going to be approximately 3.14 meters. Okay, now 160 degrees is a certain portion of that circle. Okay, so what we have is a full circle is 360. So let's just round this to 160. Make it a nice even number. Why not? So we have 160 of 360 degrees, And so that's what fraction of the circle we have here that we're in this arc. And so we're going to take that, we're going to multiply that times 3.14 meters and see what we get. Well, what happens when I take this and I divide it by 360 and then multiply that by 3.14? Now you'll notice that I took the entire number that I had in my calculator already to get the most accurate answer here, even though I wrote 160 here. Okay, and I get 1. If I round this to the nearest hundredth, I'm getting 1.40 meters, right? So I say this is approximately 1.40 meters. Okay, hopefully you have answers in your book. Okay, now let's go back here and let's remember I made an assumption here. I made this assumption that if I drew this line and it was exactly tangent to this circle, right, that was correct, right? And that's how I came up with this distance. Now, if that's not true, this distance is wrong. And then everything else is wrong. Okay? So let's look at a different assumption. Okay, now this assumption, of course, used this property, this value here. Because, like I said, I'm looking at this and I said, this doesn't really look like a 160-degree angle. I'm not entirely convinced, because 180 is, of course, a flat line that would only make this 10 degrees on one side, 10 degrees on the other. Well, I don't know. We'll see. But otherwise, all the other math after that assumption is perfectly valid. Okay, so let's just start right over. I think what I did here is I started on the second question here with the length of the second slide. That's okay. So let's start over here. I'm going to erase all this work. Okay, and I will show you another way that we can do this by making a different assumption, and it's going to give us a very different answer. And we won't actually wind up using the cosine law either. We'll be using some more basic trig, although we could use the cosine law. Okay, so let's just go ahead and erase all this. Okay, there we go. Don't need any of that. All that work. All right. So the first way that I started looking at this problem was I thought, I have all these circles here. I don't know what these circles are. I'm not an iron worker. I'm not sure what this diagram is supposed to represent. I'm just a math guy, pure math guy. And I thought, you know what? Those circles all look equidistant, meaning they all look like they're the exact same distance apart. So if I were to draw a line from here to here, and then I were to draw a line from here to here, that those two lines look like they're the same distance. And even from, say, here to here, I didn't draw that one very well. Okay, and then draw another line, say, from here to here. Draw another line from here to here. Okay, that's not a very good line. That. And draw another one from here to here. I thought, well, these look like they're all the same distance, right? And if that's true, what I have here is I have a regular hexagon, okay? Now, and this would be the center of the regular hexagon, okay? Now, if I were to draw lines from the center of the regular hexagon out to those points, okay, they're all equidistant apart. Okay, and actually what I'll do is I'll make these a different color. Let's make this red. Okay, so I'm just making triangles. And the sides of these triangles that are in red are all radii, right? So they're all the exact same length. They're all half a meter, half of the diameter. We talked about that earlier. Okay, so these are all isosceles triangles for sure. We might be able to say they almost look like, honestly, like they're equilateral triangles. Well, let's talk about this. If these are all the same distance, they all have the same base. I have similar triangles here. These are all the exact same triangles. So I've divided this hexagon up into 6 perfectly even triangles. Well, if you look in the center here, what do I have? Well, I have 360 degrees. This angle is going to be the same in every single case, though, right? So how many angles is that? Well, that's 6 angles. And what's 360 divided by 6? Well, it's 60 degrees. Now you can see why I got a different answer here, because that's a triangle that I drew using the first assumption, the first method, and I had a very different answer. I had 160 degrees here. Now I'm saying this looks like it's 120 degrees, right? Okay, well, I want to know the length here. Well, I happen to know here that this is 0.5 meters, and this one I'll do in meters. Okay, and that this is 0.5 meters. And just using basic trigonometry, this is my hypotenuse. This is my opposite side. So if you might remember this from high school, SOHCAHTOA, right? SOHCAHTOA. And with SOHCAHTOA, I'm using SAW. I have the opposite. I have the hypotenuse. What does that tell me? That tells me that the sine of 60 degrees is equal to my opposite side over 0.5. Okay, or that the opposite side in this case is, which is half of the distance I'm looking for, is equal to 0.5 times sine of 60. Okay, well, what is that? Well, let's pull out our calculator here, and let's say 0.5 times, I believe in this calculator I have to punch in 60 first and then hit the sine button. Yep, that's true, okay. And what is that? That's 0.433. But if you go over to this triangle over here, you're going to see I'm going to wind up doing the exact same thing. Here's 60 degrees, here's 0.5 as the hypotenuse, here's the opposite side. So I'm just going to double that. So in fact, it makes that 0.5 obsolete. So let's just multiply this times 2. I get essentially sine 60, 0.866 as the length of my chord. Now here's the only problem I have with this method. Well, one, I had to make an assumption. Again, both methods I have to make an assumption. I don't like that. I don't like making assumptions, okay? But I couldn't find any other way to solve this problem without making certain assumptions. Well, what I don't like about this method is that I didn't use this piece of information at all. And I won't, in fact. Because to find the chord length, I already have the angle, 120 degrees. In fact, if all these are 60, that is exactly 1/3 of the circle. Okay? And we had already said, well, the circumference of the circle, let's do this one in green. Okay, circumference of the circle we said was pi times its diameter. Okay, we had here, this doesn't change no matter what the assumption is. If you want the diameter is 1 meter, then our circumference is equal to pi times 1 meter. And if you're using 3.14, that is 3.14 meters. Okay, so that's an approximation. And if we're dealing with 1/3 of the circle here, which we are, if these are all equal, I mean, you can think about this. Here is 1/3 of a circle here, right? There's the next third, there's the next third. If they're all 60 degrees, that's exactly 1/3 of that circle. That would make your arc length so I don't even have to set up the proportion here. Length, okay, exactly equal to 1/3 of 3.14 meters. Right, so I take my 3.14 and simply divide by 3. Okay, to get 1.047 if I round. Okay, 1.047 0.047 meters. Okay, so two different assumptions, two very different answers, and that is problematic. Okay, so as I said before, you're going to want to have a conversation with your professor, maybe your classmates, to talk about this, because this problem, of course, also is given to me way out of context. Or if you do have solutions from the manual, maybe the solutions either from the first or second method line up. Either way, there's a video for you, and let me know.